For centuries, we thought galaxies were scattered randomly across space, like sand grains tossed across a beach, with no rhyme or reason to their placement. We imagined the cosmos as a vast, dark ocean with island universes floating independently, each one isolated in the void. Then, in the 1980s, astronomers did something that changed everything. They zoomed out. What they saw wasn't random at all. The universe, it turned out, has an architecture, a hidden structure on scales so enormous that we'd never noticed it before. Galaxies aren't scattered randomly. They're organized into massive walls, sheets, and filaments that stretch across hundreds of millions of light years. Between these structures lie voids so large and empty that if you lived in one, you might think the universe contained no other galaxies at all. This discovery fundamentally changed how we understand the cosmos. But it also raised a troubling question that cosmologists are still grappling with today. What other massive structures exist beyond what we can see? And how did they get there? Before the 1980s, astronomers had a fairly simple picture of how galaxies were distributed across space. They thought of them as island universes, a term that perfectly captured the prevailing view. Each galaxy was its own isolated system, floating independently through the cosmos with no particular relationship to its neighbors. This made intuitive sense. When you look at stars in the night sky, they appear scattered randomly. Some areas have more stars, some have fewer, but there's no grand pattern organizing them into shapes or structures. Astronomers assumed galaxies work the same way on a larger scale. Sure, you might find a few galaxies clustered together here and there. Our own Milky Way is part of a small group called the Local Group, but these were thought to be exceptions rather than the rule. Edwin Hubble's groundbreaking work in the 1920s and 1930s had shown that galaxies existed everywhere. We looked. He catalogued thousands of them, scattered across every patch of sky we could observe. The universe seemed democratically distributed. No matter which direction you pointed your telescope, you'd find roughly the same number of galaxies. Astronomers expected that if you could somehow map the entire universe, you'd find this smooth distribution continued at every scale. Maybe a bit clumpier in some regions, a bit emptier in others, but fundamentally uniform. There was an assumption baked into 20th century cosmology. The universe has no large-scale organization. Galaxies cluster locally due to gravity, but beyond that, just a smooth, featureless distribution stretching to the edge of the observable universe. It was a reasonable assumption based on the data available at the time, but it was spectacularly wrong. The truth began to emerge when astronomers finally mapped thousands of galaxies in 3 dimensions. But when they did, in the early 1980s, astronomers Margaret Geller and John Huchra at the Harvard Smithsonian Center for Astrophysics began an ambitious project called the CFA Redshift Survey. Their goal was straightforward: map the 3-dimensional positions of thousands of galaxies to see how they were actually distributed in space. The technique they used was called redshift measurement. When galaxies move away from us due to the universe's expansion, the light they emit gets stretched to longer, redder wavelengths, similar to how an ambulance siren drops in pitch as it drives away. By measuring how much a galaxy's light has been redshifted, astronomers can calculate its distance. It's like having a cosmic ruler that works across billions of light years. Geller, Huchra, and their team measured the redshifts of galaxy after galaxy, painstakingly building up a 3-dimensional map of our cosmic neighborhood. It was tedious work. Each galaxy required careful observation and analysis, but as they plotted more and more galaxies on their maps, something unexpected started to emerge: patterns. The galaxies weren't scattered randomly at all. They were arranged in structures, long filaments and thin sheets that stretched across space. Like a cosmic spiderweb, these structures connected to each other at nodes where galaxy clusters formed. And between the filaments and sheets lay something equally striking: enormous, empty regions called voids, containing almost no galaxies at all. At first, the team wondered if they were seeing instrumental artifacts or selection effects. Maybe their telescopes were playing tricks on them. But as they added more galaxies to their survey, the patterns only became clearer and more pronounced. This wasn't an observational error, it was real. The universe was structured. Geller and Huchra realized they were on the verge of a major discovery. The filaments they were mapping stretched for hundreds of millions of light years, scales so vast they challenged everything astronomers thought they knew about cosmic evolution. And this was just the beginning. The most spectacular structure, which would soon be called the Great Wall, was still waiting to be revealed in their data. They were seeing the first hints of what we now call the cosmic web, a universe organized like foam or a neural network, with matter concentrated in thin walls and filaments surrounding vast empty voids. It was beautiful, intricate, and completely unexpected. Then came 1989 and the image that changed everything. Geller and Huchra published a slice through their three-dimensional map, a thin wedge showing galaxy positions across a specific region of space. The plot showed thousands of galaxies, each one a tiny point arranged across hundreds of millions of light years. When astronomers saw it, they were stunned. The pattern looked like a stick figure. Galaxies weren't just organized, they were organized in a way that seemed almost deliberate. They traced out thin sheets and filaments that looked eerily like walls or boundaries. The longest of these structures stretched across more than 500 million light years, forming what the team called the CFA2 Great Wall. It contained thousands of galaxies arranged in a thin sheet, like a cosmic membrane. But what made the image truly striking were the voids, the empty spaces between the structures. These weren't just regions with fewer galaxies. They were enormous bubbles of near emptiness, each one spanning 100 to 300 million light years across. If you could somehow stand inside one of these voids and look around, you'd see almost nothing, perhaps a handful of isolated galaxies scattered across an almost empty expanse. The scale was difficult to comprehend. The entire Milky Way galaxy measures about 100,000 light years across. The Great Wall was 5,000 times larger. Light itself, traveling at 186,000 miles per second, would take 500 million years to cross from one end to the other. The media attention was immediate and intense. The stick figure universe appeared in newspapers and magazines around the world. The public was fascinated by the idea that the cosmos had a hidden architecture, that galaxies weren't just randomly scattered, but organized into the largest structures in the known universe. But for astronomers, the implications were profound and troubling. The universe had structure at scales nobody had predicted. The cosmological models of the time, the mathematical frameworks describing how the universe evolved, didn't account for anything like this. Worse, it wasn't clear how such enormous structures could have formed in the time available since the Big Bang. Everything astronomers thought they understood about the cosmos had just become more complicated. The discovery of the Great Wall and the cosmic web structure immediately created a crisis in cosmology. The question astronomers couldn't answer was simple, but its implications were enormous. How did this form? The universe is 13.8 billion years old, ancient by human standards, but not infinitely old. And gravity, the force responsible for building cosmic structures, works slowly. Stars take millions of years to form. Galaxies take billions. The larger the structure, the more time it needs to assemble. But the Great Wall stretched across 500 million light years. For gravity to pull that much matter into an organized structure, it would need more time than the universe had existed. It was like finding a fully grown oak tree on a planet that had only existed for a year. The math simply didn't work. The problem was even more acute than it first appeared. In the early universe, just after the Big Bang, matter was distributed almost perfectly smoothly. There were tiny density variations, regions that were slightly denser or slightly less dense than average, but these variations were minuscule, less than 1 part in 100,000. For these tiny fluctuations to grow into structures 500 million light-years across would require an almost impossible amount of gravitational amplification. Dark matter provided part of the answer. This invisible substance, which interacts only through gravity, makes up about 85% of the universe's matter. Because dark matter doesn't interact with light or normal matter through electromagnetic forces, it could begin collapsing into structures earlier than normal matter. The dark matter collapsed first, creating gravitational wells that normal matter then fell into, forming galaxies along dark matter scaffolding. But even with dark matter, the scale was shocking. Computer simulations of structure formation, even when they included dark matter, struggled to produce anything as large as the Great Wall in the time available. The universe seemed to have organized itself faster and on larger scales than theory predicted was possible. Some astronomers wondered if the cosmological models were fundamentally wrong. Others suggested that the initial density fluctuations in the early universe must have been larger than we thought. Still others proposed that we needed new physics, maybe gravity worked differently on cosmic scales, or maybe there were additional forces we hadn't discovered yet. The debate continues today, though dark matter simulations have gotten better at reproducing the cosmic web. But here's the thing, the Great Wall, as enormous as it was, turned out to be just the beginning. And this was just the beginning. The structures we've found since make the Great Wall look tiny. The universe looks like a giant spider web, or, if you prefer a more modern analogy, a neural network. Galaxies aren't just organized into a few isolated structures like the Great Wall. The entire observable universe is threaded with filaments of matter, connected at massive nodes, surrounding vast empty voids. It's a pattern that repeats everywhere we look, at every scale we can observe. But how large is this web? Does it extend throughout the entire universe? Or is it just a local phenomenon in our cosmic neighborhood? The answer turned out to be even more spectacular than anyone imagined. The cosmic web isn't just big, it's the fundamental architecture of the entire universe. From the nearest galaxies to the most distant ones we can observe, the pattern holds. Galaxies congregate in filaments and sheets, clusters form at intersections, and between them lie voids so enormous they dwarf even the Great Wall. Understanding the cosmic web changed cosmology forever. It revealed that the universe isn't just structured, it's structured in a specific, predictable way. And that structure tells us the story of how the universe evolved from a smooth, nearly featureless state just after the Big Bang to the intricate tapestry of galaxies we see today. Imagine soap bubbles packed together in a sink. The soap itself forms thin films where bubbles meet, creating walls and strands that outline the empty air inside each bubble. Now scale that up to cosmic dimensions, replace the soap with galaxies, and you've got a basic picture of the cosmic web. The web has 4 main components, each one playing a crucial role in the universe's architecture. First, there are the filaments, long, thin structures that act like cosmic highways. These filaments are where most galaxies live, strung out along threads of dark matter, like beads on a string. A typical filament might be 200 to 500 million light-years long, but only 20 to 30 million light-years wide. They contain hundreds or thousands of galaxies, all following the same basic pathway through space. Second, there are the nodes, the places where multiple filaments intersect. These nodes are home to galaxy clusters, the largest gravitationally bound structures in the universe. A single cluster can contain anywhere from hundreds to thousands of galaxies, all orbiting around a common center of mass. The Coma cluster, for instance, contains over 1,000 large galaxies and sits at the intersection of several major filaments. These clusters are incredibly dense. If you lived in a galaxy within a cluster, your night sky would be filled with neighboring galaxies, some close enough that you could see their spiral arms with the naked eye. Third, there are the sheets or walls, thin, flat structures where filaments connect to form surfaces. The Great Wall that Geller and Huchra discovered is one of these sheets. They're like cosmic membranes, with galaxies concentrated in a thin layer that might be 300 million light years across, but only 15 to 20 million light years thick. These walls outline the boundaries of the voids. And fourth, perhaps most importantly, there are the voids themselves. These are enormous bubbles of near emptiness, regions where galaxies are rare or absent entirely. Voids typically measure 100 to 400 million light years across, though some are even larger. They're not completely empty. A few isolated galaxies drift through them, but their density is only 10 to 20% of the cosmic average. If you lived in a void galaxy, the nearest other galaxy might be 50 million light years away or more. The pattern really does resemble soap foam or biological structures. Some astronomers have compared it to a neural network, with galaxy clusters acting like neurons connected by filamentary axons. Others see it as similar to the structure of cancellous bone tissue, with solid struts surrounding empty spaces. The pattern is universal in nature. It's what happens when you have material organizing around empty space, whether that material is soap molecules, bone cells, or galaxies. The cosmic web was hinted at in the CFA surveys of the 1980s and 1990s, but its true scale and ubiquity weren't revealed until the Sloan Digital Sky Survey began operating in 2000. The SDSS was revolutionary. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, it set out to map 1/4 of the entire sky and measure the distances to millions of galaxies. Previous surveys had mapped thousands of galaxies, impressive for their time, but still just scratching the surface. The SDSS would map millions. The data started coming in, and what it revealed was breathtaking. The cosmic web wasn't just a local phenomenon around the Great Wall. It was everywhere. Every direction the SDSS looked, it found the same pattern: filaments, nodes, sheets, and voids. The structure repeated at every scale, from nearby regions to the most distant galaxies the survey could detect. The SDSS created a three-dimensional map of the universe that was orders of magnitude more detailed than anything that had come before. You could zoom into specific regions and see individual galaxies arranged along filaments. You could zoom out and see how those filaments connected to form a vast network spanning billions of light years. The map showed unambiguously that the universe is organized on the largest scales, that the cosmic web isn't an exception or an anomaly, but the fundamental structure of the cosmos. The survey revealed something else too. The pattern was remarkably consistent. No matter which direction you looked, toward the constellation Virgo or Boötes or Pisces, you found the same basic architecture. This was important because it supported one of the key principles of cosmology, that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same everywhere and in every direction. The cosmic web didn't violate this principle because the web itself was universal. The SDSS continued operating for years, with improved instruments and expanded coverage. Later iterations like BOSS, the Baryon Oscillation Spectroscopic Survey, and eBOSS pushed even deeper into space, mapping galaxies billions of light years away. Today, the SDSS dataset contains measurements of over 5 million galaxies and represents one of the great achievements of modern astronomy, a comprehensive map of the universe's structure. So, how did the cosmic web form? How did the universe go from an almost perfectly smooth state just after the Big Bang to this intricate web of filaments and voids? The answer lies with dark matter, the invisible sculptor of cosmic structure. In the immediate aftermath of the Big Bang, the universe was hot, dense, and remarkably uniform. But it wasn't perfectly uniform. There were tiny fluctuations in density, regions that were slightly denser or slightly less dense than average. These variations were minuscule, less than 1 part in 100,000, but they were enough to set the cosmic web in motion. Dark matter was the key. Unlike normal matter, dark matter doesn't interact with electromagnetic radiation. It doesn't emit, absorb, or scatter light. It responds only to gravity. This meant that dark matter could begin collapsing into clumps much earlier than normal matter, which was still coupled to photons and prevented from collapsing by radiation pressure. As the universe expanded and cooled, dark matter started falling into the slightly denser regions created by those initial fluctuations. Gravity pulled more dark matter in, which increased the gravitational pull, which attracted even more dark matter. It was a runaway process. The rich got richer, and the dense regions got denser. These collapsing regions of dark matter created gravitational wells, invisible scaffolding that shaped the structure of the universe. And crucially, this scaffolding wasn't random. The initial density fluctuations had a specific pattern determined by quantum fluctuations in the incredibly early universe, amplified by cosmic inflation. This pattern favored structures that were long and thin, filaments rather than spheres. Normal matter followed the dark matter. Once the universe cooled enough for normal matter to decouple from radiation, it fell into the gravitational wells created by dark matter. Gas streamed along the filaments of dark matter, concentrating in the densest regions. Where the filaments intersected, matter accumulated in enormous reservoirs. Galaxies formed in these dense regions, first small dwarf galaxies, then larger spiral and elliptical galaxies as matter continued to accumulate. Meanwhile, the voids were evacuating. Matter, in the less dense regions, was gravitationally attracted to the denser filaments and nodes. Over billions of years, the voids became emptier as their matter was pulled into the surrounding web. It's like cosmic drainage, material flowing from the low-density regions into the high-density structures. This entire process has been reproduced in computer simulations with stunning accuracy. The Millennium simulation, run in 2005, tracked the evolution of 10 billion dark matter particles from the early universe to the present day. The result looked exactly like the cosmic web we observe. The Illustris project went further, simulating not just dark matter, but also normal matter, star formation, and black holes. The simulated universe it produced was virtually indistinguishable from the real one. The match between simulation and observation is one of the great triumphs of modern cosmology. It tells us we understand, at least in broad strokes, how the universe evolved its structure. Let's zoom out and appreciate just how vast the cosmic web really is. The observable universe stretches 93 billion light-years across, a distance so large it defies comprehension, and the cosmic web fills all of it. From the nearest galaxies to the most distant ones we can detect, the pattern holds. Filaments, nodes, sheets, and voids repeated across the entire observable cosmos. The filaments themselves contain most of the universe's normal matter, the protons, neutrons, and electrons that make up stars, planets, and us. Estimates suggest that roughly 50 to 60% of all normal matter resides in these cosmic filaments, concentrated in the thin threads that connect galaxy clusters. Another 30 to 40% lives in the galaxy clusters themselves. That leaves only about 10% scattered through the voids. The voids, despite containing almost no galaxies, actually make up most of the volume of the universe. If you could somehow visit a random location in the cosmos, you'd most likely find yourself in a void, surrounded by near emptiness, with the nearest galaxy millions of light years away. We live in a filament. Our Milky Way galaxy is part of the local sheet, a flattened structure of galaxies that includes our local group and neighboring groups like the Virgo cluster. This sheet is one wall of a large void called the local void. We're positioned on the edge of emptiness, looking out at a relatively dense region of the cosmic web. Everything is connected. The Milky Way is connected to Andromeda, which is connected to the Virgo cluster, which is connected through filaments to the Coma cluster, which connects to the Sloan Great Wall, which connects to structures beyond our current ability to map. It's a single, integrated network spanning the observable universe. The cosmic web is beautiful. It's elegant. It confirms our models and shows that the universe, despite its complexity, follows predictable physical laws. But the cosmic web isn't the strangest structure we've found. Because when astronomers looked more carefully at the voids, those enormous bubbles of near emptiness that make up the cosmic web's negative space, they started finding anomalies. Some voids were larger than they should be, much larger. Some were so large that they challenged the very foundations of cosmology. The cosmic web explains a lot, but it also raises troubling questions. If the universe is supposed to be homogeneous on large scales, how can there be voids that span billions of light years? How empty can empty space get? And what happens when you find voids so large that they shouldn't exist according to theory? Those questions lead us to the supervoids, regions of space so empty, so vast, that they force us to reconsider what we think we know about the universe. Empty space isn't really empty. It contains dark matter, dark energy, stray hydrogen atoms, and the occasional lonely galaxy drifting through the darkness. But some regions of the universe come remarkably close to true emptiness. These are the supervoids, and some of them are so large they shouldn't exist according to our best theories of cosmology. How big can cosmic voids get? Regular voids in the cosmic web typically measure 100 to 400 million light-years across, already mind-bogglingly large, but supervoids dwarf even these immense bubbles. Some span 1 billion light-years or more, approaching or even exceeding the theoretical limits for how large structures can be in our universe. These aren't just curiosities. Supervoids challenge the cosmological principle, the foundational assumption that the universe is homogeneous and looks roughly the same everywhere when viewed at large enough scales. If supervoids violate this principle, then something is wrong with our understanding of how the universe works. Either our measurements are mistaken, our theories are incomplete, or the universe is stranger than we thought. Let's explore 3 of the most remarkable supervoids ever discovered, each one pushing the boundaries of what cosmology says should be possible. In 1981, astronomer Robert Kirshner and his colleagues were conducting a galaxy survey when they noticed something odd in the constellation Boötes. There was a region where galaxies simply vanished. Not just fewer galaxies, almost no galaxies at all. The Boötes void, as it came to be known, measures roughly 330 million light-years in diameter. That makes it one of the largest voids ever discovered, but its size isn't what made it famous. What stunned astronomers was how empty it was. A region this large should contain about 2,000 galaxies based on the average density of the universe. The Boötes void contains only about 60. That's just 3% of the expected number, or viewed another way, the void has only 10% of the normal galaxy density. It was so empty that Kirshner nicknamed it the Great Nothing. Imagine a spherical region 330 million light-years across, large enough to fit thousands of structures the size of our local group, and finding it almost completely devoid of galaxies. The few galaxies that do exist within the void are scattered far apart, separated by tens of millions of light-years of near emptiness. Most are small, dim dwarf galaxies, as if even the galaxies that managed to form here were stunted by the void's extreme isolation. How did the Boötes void form? The current explanation involves an early evacuation. In the early universe, this region was already slightly less dense than its surroundings, perhaps by only a few percent. As the cosmic web formed and matter began flowing along filaments toward denser regions, galaxies in this underdense area were gravitationally attracted outward toward the surrounding walls of the void. Over billions of years, the void evacuated. Galaxies either moved out toward the edges or never formed in the first place due to the lack of dense gas clouds. And the void is still growing. As the universe expands, the Boater's void expands with it, becoming even emptier over time. The few galaxies still within it are slowly drifting toward the walls, pulled by the gravitational attraction of the denser structures outside. Here's a sobering thought. If we lived in a galaxy within the Boater's void, we might not have discovered that other galaxies existed until the 1960s. The nearest galaxies would be so far away and so dim that early telescopes wouldn't have detected them. Edwin Hubble's revolutionary discovery that spiral nebulae were actually distant galaxies might have been delayed by decades. Our entire understanding of the universe would have developed differently, shaped by the profound isolation of living in the great nothing. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie announced a discovery that was both exciting and unsettling. We might be living in a supervoid. And not just any supervoid, one of the largest ever detected. The KBC void, named for its discoverers, is approximately 2 billion light-years across. That's 6 times larger than the Boater's void and nearly 5 times larger than the scale at which the universe is supposed to become smooth and homogeneous. Our local group of galaxies, along with thousands of neighboring galaxies, appears to be located in or near this enormous underdense region. The void isn't as empty as the Boater's void. It has about 20% less mass than the cosmic average, rather than 90% less. But its size is what matters. A 2 billion light-year void is on the edge of what cosmology allows. According to the team's measurements, we're positioned somewhere in the outer regions of the void, not at the center, which explains why we see plenty of galaxies around us despite living in an underdense region. If the KBC void is real, it could explain one of the most vexing problems in modern cosmology, the Hubble tension. The Hubble constant measures how fast the universe is expanding. When astronomers measure this expansion rate using distant galaxies and supernovae, observations that sample the universe billions of light-years away, they get one value. But when they measure it using the cosmic microwave background radiation from the early universe, they get a different value. The two measurements disagree by about 9%, and the discrepancy has persisted despite increasingly precise observations. Here's where the KBC void comes in. If we're located in a large underdense region, local measurements of the expansion rate would be skewed. Light from distant galaxies passes through the void on its way to us, and the void's underdensity affects how that light travels. The expansion rate would appear faster locally than it actually is on cosmic scales. Being in a void could create exactly the kind of measurement discrepancy astronomers observe. But there's a problem. Not everyone agrees the KBC void exists. Some follow-up studies have confirmed the presence of an underdense region around us. Others have found no significant deviation from average cosmic density. The controversy continues, with papers published on both sides of the debate. Part of the difficulty is that measuring the void requires extremely accurate distance measurements to thousands of galaxies, and different datasets sometimes give contradictory results. If the KBC void is real, it has profound implications. It means we don't live in a typical location in the universe, which would complicate efforts to understand cosmic expansion and dark energy. If it's not real, then the Hubble tension needs a different explanation. Perhaps new physics, or unknown systematic errors in our measurements. Either way, the question remains open, and the KBC void sits in a strange limbo between discovery and skepticism. Some voids announce themselves through absence, regions where galaxy surveys find almost nothing. But one of the most intriguing supervoids was discovered in reverse, through its effect on the cosmic microwave background radiation from the early universe. In 2004, NASA's WMAP satellite produced a detailed map of the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. The CMB is remarkably uniform, varying in temperature by only about 1 part in 100,000 across the sky. But in one region, in the constellation Eridanus, there was a cold spot about 10 degrees across, roughly 20 times the diameter of the full moon. The temperature there was about 70 microkelvins colder than the surrounding sky. A tiny difference, but statistically significant and unexplained. The cold spot became one of the mysteries of modern cosmology. Some speculated it might be a portal to another universe, a remnant of cosmic inflation, or evidence of exotic physics beyond the standard model. But in 2015, astronomers found a more prosaic explanation: a supervoid. The Eridanus supervoid, as it's now called, is located about 10 billion light-years away and measures roughly 1.8 billion light-years across. It's 20 to 30% less dense than its surroundings, not as empty as the Buta's void, but substantially underdense over an enormous volume. The supervoid creates the cold spot through something called the integrated Sachs-Wolf effect. Here's how it works. Photons from the cosmic microwave background have been traveling toward us for 13.8 billion years, passing through all the structures that formed along the way. When a photon falls into a gravitational well, like a galaxy cluster, it gains energy and blue shifts. When it climbs out, it loses energy and redshifts. Normally, these effects cancel out. The photon gains as much energy falling in as it loses climbing out. But in an expanding universe with dark energy, the gravitational wells themselves are changing over time. A void is essentially a negative gravitational well, a hill rather than a valley. As photons from the CMB climb out of the Eridanus supervoid, they lose energy. And because the void is expanding, the gravitational hill's getting shallower as the photons climb it. They lose more energy than they'd gain from falling in, resulting in a net redshift. This makes the CMB photon slightly cooler in that direction, creating the cold spot. The explanation is elegant, and many astronomers consider the case closed. The supervoid provides a natural explanation for the cold spot without requiring any exotic physics. But the debate isn't entirely settled. Some cosmologists argue that even a void as large as the Eridanus supervoid shouldn't produce a cold spot quite as pronounced as what we observe. The integrated Sachs-Wolf effect should create a smaller temperature depression. Others have questioned whether the supervoid is even located at the right distance to explain the cold spot. Different surveys have given slightly different measurements of the void's position and size. Like the KBC void, the Eridanus supervoid sits at the intersection of confirmed observation and theoretical controversy. All three of these supervoids share a common issue: they're uncomfortably large. The cosmological principle, one of the foundational assumptions of modern cosmology, states that the universe is homogeneous and isotropic on large scales. This doesn't mean the universe looks the same everywhere at every scale. Obviously, Earth is different from empty space, and the solar system is different from intergalactic voids. But the principle states that if you zoom out far enough, the universe should look smooth. All the lumps and bumps, galaxies, clusters, filaments, and voids should average out to a uniform cosmic density. The question is, how far do you need to zoom out? Based on observations of the cosmic web and theoretical calculations of structure, formation, cosmologists have determined that the universe becomes homogeneous at scales of about 400 million light-years. Beyond this homogeneity scale, you shouldn't find structures that are significantly overdense or underdense compared to the cosmic average. But the KBC void is 2 billion light-years across, 5 times the homogeneity scale. The Eridanus supervoid is 1.8 billion light-years across, about 4.5 times the limit. Even the Buta's void, at 330 million light-years, is uncomfortably close to the theoretical maximum. This creates a dilemma. Either the cosmological principle is wrong, or these structures aren't as large or as significant as they appear, or we need to revise our understanding of what homogeneous means at cosmic scales. Most cosmologists lean toward the third option, They argue that supervoids are rare but not impossible, statistical outliers that push the boundaries of theory without breaking it. In a universe as large as ours, you'd expect a few structures that exceed typical sizes just due to random chance. The supervoids might be these rare, extreme examples, but it's concerning. The cosmological principle isn't just a nice idea, it's built into the mathematics of general relativity and the Big Bang model. If large-scale structure violates homogeneity more severely than expected, it could mean our cosmological models need adjustment. It might affect our calculations of dark energy, the age of the universe, or the ultimate fate of the cosmos. The supervoids remain a puzzle. They're real. We can measure them, map them, and study their properties, but they exist in tension with theory, pushing against the limits of what our models say should be possible. Supervoids challenge our theories, but at least they're empty space. You can rationalize them as statistical flukes, regions where the cosmic web happened to create unusually large bubbles. They're unsettling, but not catastrophic for cosmology. But what about structures made of matter? What happens when you find not a void, but a concentration of mass, galaxy clusters, filaments, walls of galaxies, assembled into structures so massive and so large that they make even the supervoids look small? Those structures exist, and they definitely shouldn't. In 2021 and 2024, astronomers found structures that broke the rules, not bent them, not pushed them to their limits, broke them outright. These weren't voids, regions of emptiness that might be explained away as statistical anomalies. These were concentrations of mass, walls of galaxies, arcs of matter, and ring-shaped configurations spanning billions of light years. What are these rule-breaking structures, and why do they challenge everything we thought we knew about cosmology? They're too large. According to our best theories of structure formation, there's a maximum size that any cosmic structure can achieve in the 13.8 billion years since the Big Bang. Gravity works at a finite speed, matter takes time to organize, and the expansion of the universe works against the formation of structures beyond a certain scale. The theoretical limit, calculated based on the cosmological principle and structure formation timescales, is about 1.2 billion light years, but the structures we're about to explore are 2, 3, even 4 times larger than that limit. They exist, we can measure them, and we have no idea how they formed. Let's start with a structure that, while enormous, at least falls within the realm of theoretical possibility. Barely. The Sloan Great Wall was discovered in 2003, buried in the flood of data from the Sloan Digital Sky Survey. Astronomer J. Richard Gott III and his colleagues noticed that several galaxy superclusters aligned in a long, thin filament stretching across a vast region of space. When they mapped it completely, they realized they'd found something extraordinary. The Sloan Great Wall measures 1.37 billion light-years long. To put that in perspective, light leaving one end of the structure would take 1.37 billion years to reach the other end, traveling at 186,000 miles per second, covering 6 trillion miles every year for more than a billion years. The structure is relatively thin compared to its length, only about 100 million light-years wide, making it a cosmic filament of almost incomprehensible scale. The wall isn't solid matter, of course. It's a chain of galaxy superclusters, collections of galaxy clusters linked by filaments. The structure contains over 10,000 galaxies, ranging from small dwarfs to massive ellipticals. All told, the total mass is trillions of times that of our Milky Way galaxy, and it's located about 1 billion light-years from Earth, which means we're seeing it as it was a billion years ago. When the Sloan Great Wall was discovered, it immediately became one of the largest known structures in the universe. It dwarfed the CFA2 Great Wall that Margaret Geller and John Huchra had found in 1989, and it approached the theoretical limits of how large a structure could be. Some cosmologists worried that it might even exceed those limits. But after careful analysis, Most agreed it was just barely permissible under standard cosmology. It was a relief. The universe seemed to be playing by the rules, even if it was pushing them to their absolute maximum. But structures got bigger, and when they did, the rules stopped working entirely. In 2013, astronomers Roger Close, Luis Campusano, and their colleagues announced the discovery of something that shouldn't exist, a structure 4 billion light-years across. The Huge Large Quasar Group, abbreviated Huge LQG, is a collection of 73 quasars clustered together in space. Quasars are among the most luminous objects in the universe, supermassive black holes at the centers of galaxies, actively feeding on surrounding matter. As material spirals into the black hole, it heats up and emits enormous amounts of radiation, making quasars visible across billions of light-years. What made the Huge LQG special wasn't just the quasars themselves, but their arrangement. All 73 quasars are at roughly the same distance from Earth, about 9 billion light-years away, meaning we're seeing them as they were 9 billion years ago when the universe was less than 1/3 its current age, and they're grouped together in space, occupying a region that spans 4 billion light-years. 4 billion light-years? That's more than 3 times the theoretical maximum size for a structure at that epoch in cosmic history. The discovery immediately sparked controversy. The cosmological principle states that the universe should be homogeneous at scales beyond about 1.2 billion light-years. A structure 4 billion light-years across violates this principle dramatically. It's not just slightly larger than expected, it's 3 to 4 times larger than should be possible. Some astronomers questioned whether the Huge LQG was a real structure or just a chance alignment. Maybe the quasars weren't actually associated with each other. Maybe they just happened to be at similar distances and appeared grouped when projected onto the sky, the way stars in a constellation appear grouped even though they're at vastly different distances. But the team ran rigorous statistical analyses. They calculated the probability that 73 quasars would cluster this tightly by random chance. The odds were extraordinarily low, far less than 1%. The Huge LQG appeared to be a real, physically associated structure. If it's real, it shouldn't be possible. Gravity would need more than 13 billion years to organize matter across such a vast scale. The structure would have had to begin forming when the universe was only a few 100 million years old, long before galaxies and quasars even existed. The dark matter scaffolding that guides structure formation should never have created a node this large. And yet, there it is. 73 of the brightest objects in the universe, all clustered together, all defying the rules. The debate continues. Most cosmologists remain skeptical, but acknowledge they can't easily dismiss the evidence. The Huge LQG exists in an uncomfortable space between observation and impossibility. Then, in 2021, the impossible got worse. Alexia Lopez, a PhD student at the University of Central Lancashire, was analysing quasar absorption spectra, the dark lines that appear in quasar light when it passes through intervening gas clouds. Different elements create different absorption signatures, and by studying these signatures, astronomers can map where matter is concentrated between us and distant quasars. Lopez was specifically looking at magnesium-2 absorption lines. Magnesium-2, singly ionized magnesium, is a good tracer of galaxies and galaxy groups because it's commonly found in the gas surrounding galaxies. When quasar light passes through or near a galaxy, it picks up Mg2 absorption features. As Lopez plotted the locations of Mg2 absorbers at a specific distance, about 9.2 billion light-years away, a pattern emerged. The absorbers weren't randomly scattered. They formed an arc, a curved structure sweeping across the sky. The giant arc, as it became known, spans 3.3 billion light-years across and subtends about 20 degrees on the sky, roughly 40 times the diameter of the full moon. The structure contains galaxies and galaxy clusters arranged in a graceful curve, like a cosmic rainbow frozen in space and time, 3.3 billion light-years, nearly 3 times the theoretical maximum, and located at a distance where we're looking back to when the universe was only 4.6 billion years old, barely 1/3 its current age. The universe shouldn't have had time to build something this large by that point in its history. The arc shape itself is puzzling. Most large-scale structures in the cosmic web are linear filaments or flat sheets. Arcs and curves are rare and usually much smaller. What process creates an arc-shaped structure billions of light-years across? There's no known mechanism that would naturally produce this geometry at such scales. Lopez and her colleagues ran the statistics. The probability of finding such a structure by chance is extremely low. The giant arc appears to be real, not a projection effect or statistical fluke. It violates the cosmological principle dramatically. It formed too early and grew too large. By all rights, it shouldn't exist, but it does. Lopez wasn't done. In 2024, she announced another discovery in the same region of the sky, and this one was even stranger. The Big Ring is a ring-shaped configuration of galaxies and galaxy clusters located 6.9 billion light-years away. It measures 1.3 billion light-years in diameter, which would make it merely very large rather than impossibly large, except for its shape and its location. Like the giant arc, the Big Ring was detected using magnesium-2 absorption in quasar spectra. The Mg2 absorbers trace out a nearly circular structure in 3-dimensional space. It's not a perfect ring. There are gaps and irregularities, but the overall configuration is unmistakably ring-like when viewed from certain angles. Ring structures are even rarer than arcs in cosmology. We occasionally see ring galaxies formed when one galaxy passes through another, but those are tiny, 100,000 light-years across at most. A ring 1.3 billion light-years in diameter. There's no known process that creates rings at that scale, and here's what makes it truly bizarre. The Big Ring is in the same patch of sky as the giant arc, and it's near other large structures including the huge LQG. All of these impossibly large structures are clustered in the same general region of space. Either we're extraordinarily unlucky, finding the only region of the universe where such structures exist, or there's something fundamentally unusual about this region, or about the universe itself. Lopez and her team calculated the probability that the Big Ring is a random fluctuation. It's less than 1%. Combined with the giant arc and the huge LQG, the clustering of these enormous structures in one region of space has a probability far smaller than that. The Big Ring appears to be real. It challenges everything we know about structure formation, and we have no explanation for how it formed or why it has the shape it does. So what's going on? Multiple explanations have been proposed, ranging from mundane to revolutionary. The most conservative explanation is projection effects. Maybe these aren't single structures, but multiple overlapping structures at different distances that happen to line up from our perspective. When you look at a 3D structure in a 2D projection, you can create illusions of connectivity and shape that don't exist in reality. This could explain some of the apparent sizes and geometries. But the astronomers who discovered these structures have accounted for projection effects in their analyses. They've mapped the structures in 3 dimensions using redshift measurements. The giant arc and Big Ring appear to have real physical extent in 3D space, not just apparent extent in the sky. Another possibility, statistical flukes. In a universe as large as ours, rare events will occasionally happen. Maybe we're just unlucky, finding the handful of regions where random fluctuations created structures slightly larger than theory predicts. Most cosmologists find this unsatisfying. The structures aren't just slightly larger, they're dramatically larger, and several of them cluster together. A more radical possibility, the cosmological principle is wrong. Maybe the universe isn't homogeneous at large scales after all. Maybe there are genuine structures that extend across billions of light years, organized in ways we don't understand. This would require major revisions to cosmology, but it wouldn't necessarily break physics, just our assumptions about how the universe is organized. Some physicists have suggested even more exotic explanations. Roger Penrose's conformal cyclic cosmology proposes that our universe is one in a series of cosmic epochs, each one emerging from the collapse of the previous universe. In this model, structures might carry over from one epoch to the next, explaining why we see structures that appear too old or too large for our current cosmic age. Most astronomers urge caution. These discoveries are recent, based on limited data sets, and need confirmation from independent observations. We should wait for more data before concluding that cosmology is in crisis. Future surveys, particularly the Vera Rubin Observatory and the Euclid Space Telescope, will map large-scale structures with unprecedented precision and should either confirm these giant structures or reveal them as artifacts of limited observations. But the discoveries keep coming, and each one pushes further against the theoretical limits. The giant arc broke the rules. The Big Ring broke them further. The huge LQG seemed impossible when it was discovered. But there's one structure that dwarfs even these. A structure so large that it was initially dismissed as impossible, so vast that light takes 10 billion years to cross it. A structure that, if real, would require us to fundamentally rethink how the universe forms its largest patterns. It was found by accident, revealed through the distribution of gamma-ray bursts, the death explosions of massive stars across the cosmos, and it bears a name that reflects both its location and its staggering scale: the Hercules Corona Borealis Great Wall. This is where the impossible becomes undeniable. The largest structure in the known universe was hidden in plain sight for decades. Not hidden because it was too faint or too distant, but hidden because no one thought to look for structures at that scale. It took a flash of light from 10 billion years ago, the violent death of a massive star, to reveal what had been there all along. How was this structure discovered? And what makes it so special that its very existence calls into question our understanding of cosmic evolution? The Hercules Corona Borealis Great Wall, if it's real, is 10 billion light-years across. That's not a typo. 10 billion light-years, a distance so vast that light itself, traveling at 186,000 miles per second, would take 10 billion years to cross from one end to the other. It's the largest known structure in the universe, exceeding the theoretical maximum size by a factor of 8. And it was discovered not by mapping galaxies, but by studying some of the most violent explosions in the cosmos: gamma-ray bursts. In 2013, astronomers Istvan Horváth, John Hakkila, and Zsolt Bagoli were analyzing the distribution of gamma-ray bursts across the sky. They weren't looking for giant structures. They were simply trying to understand whether GRBs were randomly scattered or showed any clustering patterns. Gamma-ray bursts are among the most energetic events in the universe. They're the death explosions of massive stars, stars at least 20 to 30 times the mass of our Sun, that collapse into black holes at the end of their lives. In their final moments, these dying stars emit a beam of gamma rays so intense that we can detect them from billions of light years away. A single gamma ray burst can release more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. Because GRBs trace the locations of massive stars, and massive stars form in regions with high concentrations of gas and matter. GRBs can potentially reveal where matter is clustered in the distant universe. If you see a cluster of GRBs at similar distances and in similar directions on the sky, you might be seeing a concentration of matter, a large-scale structure. That's exactly what Horváth, Hakkila, and Bagoli found. They noticed that a group of gamma-ray bursts weren't randomly distributed. Instead, they were concentrated in a specific region of the sky, in the direction of the constellations Hercules and Corona Borealis. When they measured the distances to these GRBs using their redshifts, they found something remarkable. The bursts were all at roughly the same distance, about 10 billion light-years away. The team performed rigorous statistical analyses. They calculated the probability that this clustering could occur by chance. The odds were vanishingly small, far less than 1%. The GRBs appeared to be tracing a real physical structure, an overdensity of matter at a specific location in space and time. When they mapped the full extent of the clustering, they were stunned. The cluster of GRBs spanned an enormous region of the sky, and when translated into physical distance at that redshift, it implied a structure roughly 10 billion light-years across. They named it the Hercules Corona Borealis Great Wall, after the constellations where it appeared, and they published their findings, knowing that what they'd found was either one of the greatest discoveries in cosmology, or a statistical mirage that would crumble under scrutiny. 10 billion light-years across. Let's pause and try to comprehend that scale, because the human mind isn't equipped to naturally grasp distances this large. Our Milky Way galaxy, which contains 200 to 400 billion stars, measures about 100,000 light-years across. The Hercules Corona Borealis Great Wall is 100,000 times larger than our galaxy. If you scaled the Milky Way down to the size of a penny, the HCGB Great Wall would be a mile wide. The local group, the collection of about 80 galaxies including the Milky Way and Andromeda, spans roughly 10 million light-years. The HCGB Great Wall is 1,000 times larger than the local group. The Laniakea supercluster, the massive structure containing our local group and about 100,000 other galaxies, measures 520 million light-years across. The HCGB Great Wall is 19 times larger than our entire supercluster. The Sloan Great Wall, which was the largest known structure when it was discovered in 2003, stretches 1.37 billion light-years. The HCGB Great Wall is more than 7 times larger. Put another way, the Hercules Corona Borealis Great Wall is about 7,000 times larger than the Milky Way galaxy. It's 20 times larger than what was previously considered the largest structure in the universe. Light takes 10 billion years to cross it. That means if a photon left one end of the structure when the universe was only 3.8 billion years old, before Earth even existed, before most of the stars in the Milky Way had formed, it will only now, 10 billion years later, be reaching the other end. And here's what makes it truly mind-bending. We're seeing this structure as it was 10 billion years ago, when the universe was less than 4 billion years old. The structure had already formed by that point. Somehow, in just 3 to 4 billion years after the Big Bang, gravity had organized matter across 10 billion light-years of space into a coherent structure. How could a structure this large form so early? According to everything we understand about structure formation, it shouldn't be possible. In 2010, astrophysicists Jatush Yadav, J.S. Bagla, and Nishikanta Kandai published a paper calculating the theoretical maximum size for cosmic structures based on the cosmological principle and our understanding of how structure forms in an expanding universe. Their calculation was straightforward. The cosmological principle states that the universe is homogeneous at large scales, smooth and uniform when you zoom out far enough. Based on observations of the cosmic microwave background and the distribution of galaxies, they determined that this homogeneity scale is reached at about 370 to 400 million light-years. Beyond this scale, you shouldn't find structures that are significantly denser or less dense than the cosmic average. They also considered structure formation timescales. Gravity pulls matter together, but it works at a finite speed. Effectively, the speed of light for gravitational influences to propagate. Dark matter helps speed up structure formation because it can collapse earlier than normal matter, but even with dark matter, there are limits to how fast structures can grow. Taking all of this into account, Yadav and colleagues calculated that the maximum possible size for a coherent structure in our universe is approximately 1.2 billion light-years. The Hercules Corona Borealis Great Wall is 10 billion light-years across. That's not slightly larger than the theoretical limit. It's not even twice as large. It exceeds the theoretical maximum by a factor of 8. It's so far beyond what should be possible that if it's real, something fundamental about our cosmological models must be wrong. Gravity simply can't organize matter across 10 billion light-years in the time available since the Big Bang. Even if you assume the most favorable conditions, the largest possible initial density fluctuations, the most efficient collapse of dark matter, the fastest possible structure formation, you can't build something this large this quickly. It's like finding a skyscraper on a construction site where work started yesterday. The math doesn't work. Either the building isn't really there, or our understanding of construction is fundamentally flawed. The skepticism was immediate and intense. Many astronomers simply didn't believe the HCGB Great Wall existed. The first objection was the limited number of data points. The structure was identified based on only about 25 gamma-ray bursts, that's a tiny sample, or 25. GRBs enough to identify a 10 billion light-year structure? Or might this be a statistical fluctuation, a random clustering that looks significant but isn't really there? The second objection was more fundamental. Do gamma-ray bursts actually trace large-scale structure accurately? GRBs mark the locations of massive stars, and massive stars form in galaxies, and galaxies trace the cosmic web. So, in principle, yes, GRBs should reveal structure. But GRBs are rare events, and the connection between their distribution and the underlying matter distribution might not be as straightforward as assumed. Maybe GRBs have biases we don't understand. Maybe their clustering doesn't reliably indicate a physical structure. Follow-up studies produced mixed results. Some studies found evidence supporting the existence of an overdensity of matter in the Hercules Corona Borealis region at that distance. Galaxy surveys showed slightly more galaxies than expected in that patch of sky at the appropriate redshift. These findings seem to confirm that something was there, but other studies found no significant structure. Some analyses of galaxy distributions showed no overdensity at all, just normal cosmic web filaments, nothing exceptional. These studies suggested the HCGB Great Wall might not exist as a single coherent structure. Perhaps it's multiple smaller structures at slightly different distances that happen to overlap when projected onto the sky. Or perhaps it's just a statistical fluctuation that disappeared when examined with better data. A 2020 study raised particularly serious doubts, questioning whether the original statistical analysis was robust enough to support the claim of such an enormous structure. The authors argued that when you account for all the possible biases and selection effects in gamma-ray burst observations, the clustering becomes much less significant, possibly not significant at all. The original discoverers have pushed back, maintaining that their statistical analysis was sound and that the structure is real. Istvan Horvath and his colleagues have published additional papers defending their findings and arguing that follow-up observations, when properly analyzed, support the existence of the Great Wall. The debate remains ongoing. Unlike the cosmic web or even the supervoids, which are now generally accepted by the astronomical community, the Hercules Corona Borealis Great Wall exists in a state of deep uncertainty. Some astronomers consider it a real structure that challenges cosmology. Others consider it a cautionary tale about overinterpreting limited data. If the Hercules Corona Borealis Great Wall is real, the implications are profound. It would mean that our understanding of structure formation is incomplete. Something about the early universe, something we don't currently understand, allowed structures much larger than predicted to form. Perhaps the initial density fluctuations from quantum effects in the first moments after the Big Bang were much larger than we thought. Perhaps dark matter collapse faster or more efficiently than our models predict. Perhaps there are additional forces or fields we haven't discovered that aided structure formation. Or perhaps the cosmological principle itself is wrong. Maybe the universe isn't homogeneous at large scales. Maybe there are genuine structures extending across billions of light years, and our assumption of smoothness beyond a certain scale is simply incorrect. This would require major revisions to cosmological models, but it wouldn't necessarily break physics. Just our assumptions about how the universe is organized. Some physicists have proposed more exotic explanations. Varying speed of light theories suggest that, in the early universe, light traveled faster than it does today, which would allow structures to form more quickly. Others have suggested that dark energy evolved differently in the early universe, affecting the rate of structure formation. Still others point to Roger Penrose's conformal cyclic cosmology, which might predict large-scale structures carrying over from a previous cosmic epoch. Or, and this is what most astronomers believe, the HCGB Great Wall simply isn't real. It's a statistical artifact, a pattern we've imposed on random data, seeing structure where none exists. We're pattern-seeking creatures, and we sometimes find patterns even in randomness. The only way to resolve this is with better data. We need more observations of that region of space, more gamma-ray bursts, more galaxy surveys, more detailed maps of matter distribution at that distance. Future surveys will help enormously. The James Webb Space Telescope can observe galaxies at high redshift and might detect an overdensity of galaxies in the HCGB region if one exists. The Vera Rubin Observatory will map large-scale structure across the entire sky with unprecedented precision. The Euclid Space Telescope mission is specifically designed to study cosmic structure and the role of dark energy. Within the next decade, we should have a definitive answer. Either the Hercules Corona Borealis Great Wall will be confirmed as the largest structure in the universe, forcing a revolution in cosmology, or it will fade away as more data reveals it was never there at all. Here's what we need to remember. We're still mapping the universe. We've only been doing it seriously for about 30 years. The Sloan Digital Sky Survey started in 2000, just a quarter century ago. Before that, our maps of cosmic structure were based on surveys of thousands of galaxies, not millions. We had hints of the cosmic web, but we hadn't seen its full extent. The supervoids were known, but not their full scale. The giant structures, the arcs, rings, and walls that challenge our theories hadn't been discovered yet because we simply didn't have the data. The universe is 13.8 billion years old. We've barely begun exploring it. We've mapped a fraction of the observable universe in detail, and we're constantly finding surprises. The giant arc was discovered in 2021, just 3 years ago. The Big Ring was announced in 2024, months ago. Every major survey reveals new structures that push against theoretical limits. Every improvement in observational technology shows us something we didn't expect. The universe is more complex than our models predicted. It has structures larger than our theories allow. Either our measurements are wrong, which seems increasingly unlikely as independent observations confirm the basic findings, or our theories are incomplete. Or, most likely, both need refinement as we gather better data and develop more sophisticated models. But this is how science works. We're not reading from a book where all the answers are written down. We're explorers mapping unknown territory. Every discovery raises new questions. Every answer reveals new mysteries. Think about what we've learned in just 40 years. The cosmic web, the fundamental architecture of the universe, was unknown until the 1980s. Supervoids that challenge the cosmological principle were discovered in the past decade. The giant arc and Big Ring that violate theoretical limits were found in the past few years. Each discovery builds on the last, gradually revealing a universe far stranger and more structured than we imagined. What will we find in 2030? in 2040? What structures are waiting to be discovered in the next generation of surveys? Will future telescopes reveal even larger structures, pushing the crisis in cosmology to a breaking point? Or will they help us understand why these structures exist, providing new insights into dark matter, dark energy, and the earliest moments after the Big Bang? The universe is organized on scales we're only beginning to understand. From the cosmic web that threads through space to the Hercules Corona Borealis Great Wall that stretches across 10 billion light years, each structure tells us something profound about how the cosmos evolved, about dark matter's role in sculpting the universe, about the physics that operates at the largest scales imaginable. We're living in a golden age of cosmology. Technology has finally advanced to the point where we can map the universe, trace its structures, and test our theories against observation. The mysteries we're uncovering now, the supervoids, the giant arcs, the impossible walls, will keep cosmologists busy for generations. But we're still at the beginning. There's so much more to discover. Future telescopes will peer deeper into space and time, revealing structures we can't yet imagine. Some of these discoveries will challenge our theories even further, forcing us to revise or even abandon cherished ideas. Others will help us understand why the universe looks the way it does, providing answers to questions we've been asking for decades. The universe is vast, complex, and beautiful. It has hidden architectures on scales that dwarf our comprehension. Galaxies are organized into filaments. Filaments connect at nodes. Structures span billions of light years. And we're just starting to see the full picture. If these discoveries excite you, if you want to follow along as we continue mapping the cosmos and uncovering its secrets, subscribe for more cosmic discoveries, because there's always something new to find in the universe. Every survey reveals surprises. Every telescope shows us something unexpected, and the universe never stops surprising us.